Welcome back to Advanced Machine Learning. I'm Ludwig Botmann, and in this video I will explain some methods for undersampling in imbalanced datasets. In the end, you should know the idea of these sampling methods for coping with imbalanced data and especially understand some different undersampling techniques. Let's start with an overview of sampling methods. So the general idea of sampling is always to balance the training data distribution to perform better on minority classes. So as you already know, the classifier may be biased towards the majority class. So we want to, as a pre-processing step, let's say, balance the data set such that in the end the classifier is working equally well on the minority and the majority class. So these approaches are always independent of the classifier because we are doing this as a pre-processing step. It does not depend on the learner we use. There are in general three groups that we can look into. First group is undersampling. There we remove some instances of the majority class, visualized here in the upper part of that figure. So on the left hand side here is the original data set. You see that the class distribution is very imbalanced. We have a majority class and the minority class, and of course more observations of the majority class. That's why it's called majority class. And what we do in undersampling is that we make the majority class smaller. So we disregard some of those observations, and in the end the data set is more or less balanced. Alternatively, we can oversample data. So that's the second part here. Again, we have two different sizes of those classes. And now we take the smaller class and just try to come up with some new instances, or perhaps with just duplicating the instances that we have, so that in the end, again, we have a balanced data set. And of course, as a third group, we can also think about some hybrid approach that combines those methods. So now we'll speak about some undersampling methods in detail. So let's first start with some random methods for oversampling and undersampling. So continuing the overview here. So in random oversampling, we randomly replicate the minority instances, as I've seen in the last figure. This is prone to overfitting because we could end up with multiple tied instances, so with just duplicating the same instances over and over. And on the other hand side, we have random undersampling, where we just randomly eliminate some of the majority instances. Of course, eliminating instances always doesn't feel good, okay, because we might lose some information here and destroy important concepts in the data. So it would be better to introduce, if we use random undersampling, some heuristics in the removal process, and if we do oversampling, perhaps not use exact copies. So one way of undersampling, which is not random undersampling, is called Tomek links. The main idea is to remove some noisy borderline examples. So we do not want to remove just any random examples, but some examples that are called noisy borderline. So these noisy borderline examples are observations that are very close to each other but have different classes. So what we do is we define two data points. We call those EI and EJ. So just two data points from a data set, xi, yi, and xj, yj. And now we define this pair this pair now is called Tomek link if there is no other data point that is closer to one of those observations in the feature space. Okay, so for the moment we only think about x and not about y, and then two observations are called Tomek link or have a Tomek link if there is no other observation that is closer to one of those two observations here, with respect to some distance metric here, of course. So if these two observations now have differing class in the data set, so are not from the same class, so let's for a moment just think about a two-class example of minority and majority, then these pair is a noisy borderline example. And then we remove the majority instance from that pair. Okay, so first we are looking for those Tomek links for those pairs who are very close to each other. Then we look if the classes differ, and if the classes differ, then we remove one of the two observations from the data set, and that is exactly the observation that corresponds to the majority class. Okay. You can see this somehow here in this figure, and yeah, well, it's a little bit small, but perhaps if you zoom in, you can see more here. There are observations such as this minus here and that minus that do not show up in the lower plot. Okay, so this is because apparently those are Tomek links or are parts of Tomek links. So where then the true class of the pair or the two class of the two observations of the pair haven't been the same, and then we removed the majority class because the negative class is here the majority class. Okay, so far for Tomek links, there is a bunch of different undersampling techniques. So generally undersampling perhaps isn't performing that well as oversampling, but it's of course good in the sense of computation time, because if you reduce your data set, so smaller data set, you're faster of course, so these undersampling techniques have their value. And some other undersampling techniques are on this slide here. So the first one is neighborhood cleaning rule. It works as follows. First, for each observation, of course, you need a for loop here over the entire data set. You look for the 3 nearest neighbors of that observation. If the class of this observation is the majority class, and if the 3 nearest neighbor classifiers is it as minority, then you remove exactly this data point from the data set. If it's the other way around, so if it's a minority class data point and the 3 and n classifies it as majority, then of course you will not remove xi or yi, but you will remove the 3 nearest neighbors that are more or less the culprit for this wrong or this false classification. Then we have condensed nearest neighbors, CNN. So here we construct a minimally consistent subset d tilde of d. What does this mean? So d of course is the entire data set, and d tilde is a subset that is consistent in the way that the classification of a nearest neighbor, a k nearest neighbor, perhaps 1 nearest neighbor is 3, 5, 7, something like that, where the classification of all the instances in that dataset D is the same if using d tilde or d as training data for that classifier. Okay, and then it's called a consistent subset. And of course we want to have a minimally consistent subset because we want to find the smallest of such subsets. Because d tilde of course d is of course a consistent subset of itself, okay, because it will result in the same classification, but it's not smaller, so we didn't really undersample at all here. Okay, then we have one-sided selection, that's Tomek link, and after that applying the condensed nearest neighbors, or we can do it the other way around, first condensed nearest neighbors and then Tomek link. And finally we have some clustering approaches. These are class purity maximization and undersampling based on clustering.